Okay, so this is the first lecture on 455. We'll talk about slope fields and Euler's method. We're going to start this semester by doing a little review of some material from the past. So here's a differential equation. dy dt equals 1/3 y plus t squared. We can solve this. Most differential equations can't be solved, so we want to be able to develop tools that can be used for equations that can't be solved for formula. And so we'll look at slope fields and Euler's method. Just as a reminder, how to solve this using undetermined coefficients. Remember that the solution is going to be the homogeneous solution plus the particular solution. The homogeneous solution, y sub h, is the solution to this equation. It's just the part with the y. And that's y sub h equals some constant e to the 1/3 t. Particular solution is a function based on the form of the function of t there. So we'll guess that the particular solution is at squared plus bt plus c. Remember that if you have a polynomial, you guess polynomial of the same degree. If you have an exponential, you guess an exponential. If you have a sine or a cosine, you guess a linear combination of sines and cosines. So the equation, we plug yp into the equation. So we want dyp dt equal to 1/3 yp plus t squared. And if you actually plug all this in, the derivative of yp, that's all this stuff, this is my left-hand side, equals 2at plus b. The right-hand side is 1/3 yp, which is 1/3 at squared plus 1/3 bt plus 1/3 c plus the t squared that's floating around. So this is 1/3 times yp plus t squared. To be a solution, these must be equal to each other. My left-hand side is this, and my right-hand side is that. Great. So what do we actually have here? So the left-hand side is 2at plus b, but I want a 0 t squared there because there's no t squared term on the left-hand side, so the coefficient of t squared is 0. I have a 1/3 a plus 1 more t squared on the right-hand side, a b over 3t, and a 1 over 3c. So we match coefficients. Zero equals 1/3 a plus 1. So 0 here must be equal to this. And so that means that a must be -3. 2a equals b over 3. So that means b equals 6a equals -18. And b must be equal to c over 3. 3b equals c. So that means c equals -54. 3b equals c. Good. So we've found our homogeneous solution. We've found our particular solution. Y is the homogeneous solution plus the particular solution. So it's k e to the 1/3 t plus -3t squared minus 18t minus 54. That's our yp here, and that's our y sub h. So there's a solution to that. We can also solve this by integrating factors. Remember that if we have dy dt minus 1/3 y equals t squared, then our integrating factor is e to the minus integral of, no minus sign there actually, e to the integral of whatever this is, which is actually a minus 1/3. It's the coefficient of y, et. So our integrating factor is e to the minus 1/3 t. The formula using integrating factors, y equals 1 over mu, integral of mu, which is our integrating factor, times whatever's on the right-hand side, which is our t squared dt. And this becomes e to the 1/3 t, because 1 over this is e to the 1/3 t, times e to the minus 1/3 t times t squared dt. Integrating this is an integration by parts, which I will not do. But at the end of the road, you get y equals e to the 1/3 t times minus 3t squared e to the minus 1/3 t minus 18t e to the minus 1/3 t minus 54 e to the minus 1/3 t when you do all the integration by parts, plus a constant. And so if you actually multiply this part through, it'll cancel out all of the e to the minus 1/3 t's. So you pick up again the same thing, which we would hope we would. There's our particular solution plus c e to the 1/3 t. So same solution both ways. So this is a particular solution. This is a particular differential equation that can be solved. A lot of other ones can't be. So we want to be able to figure out what a slope field is, and we want to be able to graph that. So we have these formulas for solutions, but what do these kinds of curves actually look like? So we'll graph the slope field. Well, we're going to use things called isoclines and nullclines. So an isocline, and it's underlined because this is a thing we want to remember, it's a curve in the plane where dy dt is a constant. So it's the places in the plane where at every point in the plane, dy dt has the same thing. A nullcline is a curve in the plane where dy dt actually equals 0. So dy dt equals 1/3 y plus t squared. The isoclines are just the level curves of this function. In other words, if we pick a particular value of k, the curve satisfying this equation has slope k at that point. So we can do this by hand. Did click here. There we go. So what do we mean by all this? If dy dt equals slope of tangent line, but that's also equal to 1/3 y plus t squared, because it's a differential equation. Dy dt equals 0. That means slope of tangent line equals 0, which means you have a horizontal with tangent line. But that must mean that 1/3 y plus t squared equals 0. And you can solve that for y. Y equals minus 3t squared. Y equals minus 3t squared. I tried to circle that, but it didn't work. So what does that tell me? At any point in the plane that's on this graph of y equals minus 3t squared, tangent line is 0. So sketching a slope field by hand. Slope fields have t on the horizontal axis, y on the vertical axis. Y equals minus 3t squared. That's this curve, just sort of sketching it in. And all along that curve, the slope equals 0. That's our nullcline. If we want the places where the slope is equal to 1, we set the slope equal to 1, but the slope is equal to 1/3 y plus t squared. And so if we solve this for y, we get 3 minus 3t squared equals y. So it takes this curve, which is minus 3t squared, and moves it up 3. So this is the isocline where the slopes are equal to 1. And then if we take dy dt equal to minus 1, that should be equal to our right-hand side. And then that's going to be minus 3t squared equals y. So if minus 3 is down here, this is where the slope equals minus 1. That's sort of an underlying structure of this. So all along here, we draw in slope marks of tangent lines, right? A little bit of tiny tangent lines that are slope 0. All along this curve, we use little tangent lines of slope 1. And then all along this curve, we have little tangent lines of slope minus 1. Like that. So this is slope equals 0. Remember, if you're going to go from positive to negative, you have to go through 0. So inside of this parabola, all the slopes are negative. So we have sort of shallower negative slopes in here, and then steeper ones in there. Outside of this, in this direction, all the slopes will be positive. We'll sort of have shallower ones closer to the line, to the note line, where the slopes are 0. And you get steeper as you move away. So what our solution curves look like? Well, if we pick this as an initial condition here, tangent to that, just goes off like this. In backwards motion, it's going to be tangent to these, but end up dropping off like that. If we start here at 0, we have a 0 tangent line, so we start up flat, and then we start rising and rising, and getting more and more steeper that way. And back here, we get steeper going out that way. And so if we start somewhere inside of the note line, like here, our slope is actually negative. So we'll go down a little bit, hit the note line where our slope will be 0, and then start climbing out of it. And we'll go back up this way, hit the note line where the slope is 0, and then go back down that way. Note, of course, that the note line is where dy dt equals 0, slope equals 0. That means you have a maximum or minima. So the maximum minima of solutions are going to occur on the note line. So there's a sketch of it by hand and what the solutions should look like. We can do this for any differential equation, whether we can solve it or not. We can always get a picture of what solutions look like. In general, we won't be able to solve these things, but we want to be able to know what solutions look like and what they do. So this little picture that we drew tells us something, right? We have sort of two types of solutions here. One is sort of, almost like a cubic. It comes up, goes down, goes back up. And then another one is just a curve that goes, increases up. So, and there's a couple of solutions. Y of 0 equals minus 3, y of 0 equals 0, and y of 0 equals 1. GeoGebra can do much of the work for us. So we will look at GeoGebra for a minute. So let me pull that up. So here's GeoGebra. It's got a couple of nice features, one of which is just the slope field command. And generally we want this command. Remember that I generally tend to do my independent variable as t. GeoGebra requires that you use x, so that's okay. So our slope field is 1/3 y plus x squared. Oops. Slope field is 1/3 y plus x squared. And there it is. Right? And you can see I'll zoom in a little bit here. So you can see in here that there's some kind of thing going on there where the slopes become negative. And we can actually put in the nullcline. And so there's our nullcline. That's where the slopes are 0. Inside of the parabola, you can see that the slopes are all negative. Outside of the parabola, the slopes are all positive. Now, for certain types of differential equations, like this one, which is actually a linear differential equation, so it's not too hard to solve, a GeoGebra can actually solve it, right? So solve O to E. Here you give it a x value, you tell it what the equation is, and then you give an initial condition. So we want to solve ODE, and we say that our right-hand side of our differential equation is that, and we want to start, say, at 0, minus 3. And it'll think a little bit, and then, ta-da, there it is. And it actually can solve it. You can see the solution here under g of x. And so our initial condition is right there. When it can solve it, it'll actually give you a function. So g of x is the solution. It knows what that is. So you can say, okay, I want 0, g of 0. And it gives you that, and that's your initial condition, is there. The solution comes through like that. Note that the maximum minima occur on the green curve because that's my nullcline. We can ask for other solutions. 1/3 y plus x squared, start at, say, 0, 1. And that gives us another solution up here. So that's purple line, that's calling h of x. And we can also ask for just what's the solution that goes through. Oh, it's not happy. That's one of the problems with GeoGebra. Sometimes it just stops working. Hang on 1 second. Okay, I think we're back. There we go. So solve ODE. We want to solve 1/3 y plus x squared. And we'll start just at 0, 0. And so there's that solution that goes through right there. So 3 separate solutions that we can get. This can be solved. Notice that when you look at the solutions that GeoGebra is pulling out for g of x, it's minus 3x squared minus 18x minus 54. That's our particular solution, plus our exponential minus 3x squared minus 18x plus 55, e to the x over 3 minus 54, etc. So there's our various solutions to our differential equation. And we can see that there's really kind of 3 types. One is misses the nullcline entirely. That's this purple curve up here. We have one boundary condition sort of that just touches it there. We just have a point of inflection there. And then we have a maximum minimum as we look at that other one. So those are our solution curves. GeoGebra is nice like this, that it can actually plot these things. And it's, we can pick, say, g of x. That's this point. That's the solution that goes through minus 3. And we can actually plot, say, 3, g of 3. So we'll pull out a little bit. When t equals 3, g of 3 is this number, which is about 3.623. Right? That's what we have here. So now if we have a differential equation where we can't actually get the solution, how can we actually get a good estimate for what this is, for what the y value is on this curve if we don't know the formula of the curve? And that's where Euler's method will come into play. So let's look quickly at a more complicated slope field. So xy squared divided by the quantity x plus y cubed That's absolutely not what I wanted. XY squared. Have to be careful with this thing. There we go. Divided by x plus y quantity cubed. And out from the denominator there. And then we want plus sine of x minus cosine of y. Oops, minus cosine of y. So there we go. There's a slope field for kind of a weird differential equation. What do solutions look like? There's no solution to this one. We don't know how to solve this. So what we can do with GeoGebra is we can ask it to do a numerical approximation. So solve ODE, right-hand side of the equation, start where you want x, start your y, that's your initial condition. How far do you want to go to the right, and how big of a step size do you want? So we'll use this. So we'll put in, if I can do this without completely screwing it up, I already screwed it up. Divided by x plus y quantity cubed plus sine of x plus sine of x minus cosine of y. We want to start x at 0. We'll start y at 0, so our initial point will be 0, 0. We'll go to, I don't know, value 3, and we'll do a step size of 1. And we'll see what it gives us. And it says it doesn't like that at all. Start x, start y, end x. Well, let me see what's going on here. What was going on there was actually I had to use an equal sign instead of a minus sign. So I think now I actually have the correct things in there. Sine x minus cosine y, start at 0, 0, go to x equals 3, go to 1, and it doesn't actually do anything, which is a little odd. And the problem is that 1 is a little bit too big. So if we reduce the step size to 0.1, well, this worked before, so hang on a second, let me see what's going on. Well, I remember what happened there. Solve ODE, f prime of x, want this thing, x, y squared divided by the quantity x plus y cubed, and note that we can't use 0, 0 as an initial condition because everything blows up there. We'd be dividing by 0. So plus sine of x minus cosine of y. And I have to remember to make that a minus sign and not an equal sign. We'll start x at 0. We'll actually start y at 1. We'll end x at 3, and we'll take a step size of 1 and see what we get. And so there's that solution, right? And so what it did is it started here. This is Euler's method. It started at 1. It looked at the tangent line. It just went 1 unit in the direction of the tangent line, recalculated the tangent line when it got to x equals 1, went up that tangent line, recalculated the tangent line when it got x to 2, and went up that line. So there's our graph a little bit. We can do a better version of this by making the step size smaller. So instead of having a step size of 1, we can do a step size of 0 plus as 0.1. Now you get something that actually looks like a curve. You can't actually get numbers out of this because there's no function, right? When it says numerical integral, there's no actual function involved here. It's just an estimation that they did. But that gives you a feel for what that kind of curve looks like. We could, if we wanted to, extend this out from 3 to say I don't know, up to 8, say, and see how long that looks like. There's that curve. And so that gives us a solution curve. So we can get a picture of the solution curve, although we can't actually get a formula for it. So we know what the solution curve does. It looks like this. We can also, right, notice that there's some maximum minimums. We can also find out what the null line looks like. So where are all my zeros for slopes? Well, you take your right side of your equation, and that's plus sine of x minus cosine of y. You set it equal to 0, and then you hope that it can give you a sketch of that. And it does. It has to do numerical crunching to get this picture out. So the red curves are the null lines, right? So these are all where your derivatives, where your tangent lines are 0, right? And so everywhere we have a minimum on our black curve, right, that crosses a null line, cross a null line here and here. It's going to cross a null line here and go down inside here and here and here, right? Slopes are negative. Outside that, slopes are positive. There's something weird going on up there. I don't know what that is. So that gives you the null lines. If you zoom out, it has a little bit of a problem with it because it's trying to fill in the null lines, but you can sort of see what it kind of looks like. And you can see what solutions will do. They'll sort of slide through here and wander through the null lines up to the right, more or less. So we can get pictures of solutions. GeoGebra sort of does, I think it's probably more sophisticated than just Euler's method, but it does a way to approximate solutions following the slope field. And so we can get various numbers. If we wanted to know what y of 6 is, it looks like it's about 4, but you can actually approximate that pretty well. Okay, so that's GeoGebra. Oops, I'm supposed to share the screen and go back to this.